All right, good morning, everyone. Happy Halloween. Everyone's all dressed up, I see, and all ready for their midterms because they're super scary. So, we have a nice other relaxing topic today, and that is page replacement. So, hopefully, this isn't too bad. Lab 4 is released, so if you can, while that Lab 4 primer lecture is still fresh, you could probably start it and finish it after your midterms and be stress-free for 2 weeks. So that would be nice. The Quiz 2 grading is apparently happening later this week, so hopefully that comes back soon. They still haven't decided a day, but hopefully it'll be soon. All right, so today we'll be talking about page replacement. So memory and storage on your device is a big hierarchy where there's always this capacity and speed trade-off. So at the top of the pyramid, that is the fastest memory on your machine, it's your CPU, like your registers, your L1 cache, your L2 cache is next fastest beside that. And at the top, your registers are the fastest. That's where all the operations take place, but there's only a limited number of them. They're not very big. Then below that, you have your CPU cache, which is a bit bigger, like it's in the megabyte range now. It's like the 32 megabytes are the big ones. Then after that, you have memory or RAM that is, 32 gigabytes or something on that order and fairly fast. And then below that, there's going to be non-volatile memory or NVMEs, which are, your little small solid state devices that are really, really fast. Then below that are going to be your SSDs, or just plain old flash memory, which are going to be slightly slower and have higher capacities and or be cheaper. Then below that, you have hard disk drives, which are just spinning magnetic disks that are even slower, but you can buy, 12 terabyte ones quite easily, and they're fairly cheap. And then below that, there's tape drives that are still actually used. That's like what Google uses for really, really slow archival storage. So you can buy a tape that holds like 50 terabytes or something like that. But if you've ever seen the machines, you can like YouTube it. It's like a really old tape system. It'll go pick up the tape, do it in, write. Slow as hell, but it's cheap as hell as well. So all the archival storage would be on something like that, and it's still actually used, although no one will likely in this class ever see tape drives. So we have this giant hierarchy, and it's only going to be getting worse and worse over time because there's hierarchies within devices. So like your NVMe drive will have a cache on them too, and there's just going to be this whole hierarchy hidden everywhere, and you don't want to have to deal with all of it. You would ideally like each level here to pretend it has the speed of the lower level, the speed of the higher level and the capacity of the lower level. So you get kind of the best of both worlds, and you want the memory used by processes, you have some physical limitations. So all the memory used by all the processes can exceed the actual physical memory on the device. So what you can do is you can make the illusion that you have more memory by essentially using the capacity of the device below it. So in this case, if you want to make memory seem like it's even larger, you could just put some pages onto the hard drive storage and use that. So that's what we'll be talking about today, how you decide what pages go into hard drive storage and what the best policies for that would be. So what you do with that is if there are memory pages being used, you keep them in memory, while all the unused pages you can flush to disk and just keep them around in disks. So if you need them, they're still there, but it will just take some more time to access it. And then whenever you need to use that page again, you would swap it back to memory. So you would write another page out to disk and then swap in the one that was from disk back to memory, and then you can use it and have the illusion of having 32 gigabytes of RAM, even though your machine even has 8 or something like that. So there are 4 page replacement algorithms we'll talk about today. There's the optimal algorithm, which is essentially like an oracle, like you're seeing into the future. So in this case, you replace the page that won't be used in the longest. So I just throw out the page I know I'm not going to be used in the longest so that all the other pages I'm reusing over and over again, and I'm essentially getting all the cache hits for free. And then there are a few other strategies. There is a strategy of just randomness where I just randomly replace a page, which surprisingly works quite well. There's our good old friend, first in, first out, which just replaces the oldest page first. It is a very easy decision and a very easy thing to implement, but it's probably not going to be the best thing. And then the last policy is the least recently used policy. So this is something you could actually implement. And the idea here is just to replace a page that hasn't been used in the longest time, because likely nothing's using it anymore, so I can write it out to disk, and all the other pages are being used over and over again, so I'd keep them in memory. Yep.
So basically I'll use history-based, and then optimal will be prediction-based, right?
Yeah, so the question is the least recently used history-based? And yes, because you're keeping track of the least recently used. And then optimal would be essentially prediction-based, or if you're actually doing the optimal solution, it's you just look into the future, which isn't going to be possible. So we pretty much just discuss optimal just so we have a baseline to compare a bunch of different algorithms. So here is our scenario that we're going to be using the whole day. So it's a bit of a ridiculous scenario just to make things easier to write. So assume our physical memory can only hold 4 pages, and then you access this following. So we just give each page a number. So in here, there are a total of 5 pages, 1 to 5. And initially, we'll just assume all pages are on disk. So we have to bring them into memory. So this is what we'll use for all of our examples, and our goal here is we want the fewest number of page faults when we do all these accesses. So for every example, at the end of the day, we're just going to record the number of page faults we have, and we'll be recording when they happen. So let's go through a little example just to get our feet wet, and we will do the optimal example for all these accesses. So these are all our accesses. So we access page 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So if we do that, we're assuming that all of our pages are on disk and nothing in memory. So the boxes there are what is currently in memory, and they're all currently blank. So whatever we have in access to 1, so I put the accesses above the box. It is not in memory, so we have a page fault, and we have to bring it into memory from the disk. So in red, I will put the pages that we just brought into memory. So for the first access for 1, not in memory, we have a page fault, we have to load it in. Okay, and this story is going to look fairly boring for the first few. So if we access page 2 next, then it's not in memory, we have to bring it in. So we have 4 slots in our memory, so we can keep page 1 around. So we bring in page 2 as well, and now there are page 1 and 2 in memory, and that would also be a page fault. Then we have page 3, same story, it's not in memory, we can load it in, page fault, it's in red. Same story for number 4, not in memory, we bring it in, it's in red. So what happens now if I try to access, our next access is on page 1. So what happens then? I got a thumbs up. So thumbs up, everything's good. It's already in memory. I don't have to do anything. So in that case, I would just write out the same thing. Nothing's in red. There is no page fault. Nothing bad happened. It was already there. I'm nice and fast. Now we access page 2. Same thing's going to happen. It's already in memory, and we're good. We don't have to reload anything. We don't have to swap anything out. We're still living the good life. Now we have an access to page 5. So now there's access to page 5. It's not in memory, and we have to kick something out. And between page 1, 2, 3, and 4, what should we kick out? I see a 4. Everyone who thinks 4? We got a lot of 4s. 3. Okay. Do you have any 2s or 1s? Okay, so remember for optimal, you are going to replace a page that is not going to be used the longest into the future. So page 1 is going to be used in the next access right away, so we should keep that. And then we should keep page 2 because that's also going to be used in the subsequent access after that. And then we should also keep page 3 because it's used right after that. So if we want to keep around throughout the page that's going to be not used the longest, we would actually kick out page 4 because 1, 2, and 3 are all accessed before that. So when we access page 5, we're kicking out page 4. So we replace the 4 with a 5, and we wrote it in red or a different color, or you can circle it or whatever to indicate that it's a page fault, and that was our swap. So now, because we looked into the future and we saw everything, when we access page 1, that's a hit, it's already there. Access page 2, that's a hit, it's already there. Then we access page 3, it's a hit, it's already there. And now we have page 4. So now we have to replace either page 1, 2, 3, or 5. Which should we replace? So should we replace page 1? Replace page 2? Replace page 3? Replace page 5? Okay, so no one wants to replace page 5, and we were fairly ambivalent about the other ones. In this case, there's no future accesses, so you can pick whatever one you hate first. Generally, when I teach this, classes seem to hate number 1 the most, so number 1 gets kicked out. So in this case, doesn't matter. As long as you don't kick out 5, that's fine. So in this case, we kick out number 1, and we replace it with 4. And now, because we didn't kick out number 5, on our last access, we access page 5, so we are all good. It's in the cache. So the last thing we need to do is get the number of page faults. So how many page faults do we have here? 6. So you just count the number of red numbers. So we have 6 page faults. And if this is our optimal, whenever we look at any other algorithms, if this is the optimal, any other algorithm should only do at best this and can't go lower. Otherwise, that's kind of a weird contradiction. So 6 page faults is our target. Okay, well, let's go at it with a FIFO example, or first in, first out. So in this example, our first 4 page accesses are going to look exactly the same. There's nothing in memory, everything is on disk. So if we access page 1, we have to load it in. It's a page fault, page 2, page 3, and page 4. So these are our first 4 page faults, and now our memory is full, and we have the pages 1, 2, 3, and 4 in. So now when we access page 1, we get a page hit, then page 2, we get a page hit. Now something more interesting happens here when we have an access to 5. So when we have access to 5, what are we going to replace if we're doing first in, first out? 1, right? So the first page we loaded was a 1. So if we're doing first in, first out, since 1 was the first one in, way back here in step 1, then it's going to be the first one out. So when we access page 5, we replace page 1. So now we replace page 1 with page 5. So now what's currently in memory is 5, 2, 3, 4. Now we're going to access page 1, and oh no, we just kicked it out. So we're going to have to swap back in page 1, and what are we going to swap out? 2. So now 2 is the oldest one, because that was the second thing we put in. So now we're going to swap out page 2 with page 1. So now in memory are 5, 1, 3, 4. And now, unfortunately, in the next access, we're going to access page 2. So we have to swap it back in. Now 3 was the first one in between the remaining pages. So we swap back in 3. And now we have another page fault. And now in memory, we have 5, 1, 2, 4. Now we have an access to page 3. Oh no, we just kicked it out again. So now 4 is our oldest one. So we replace 4. So now in memory, we have 5, 1, 2, 3. And now our next access is to page 4, which we just kicked out again. So you can see how this was really bad. So now 5 is our oldest one that's still remaining. So we would replace 5 with 4. Now we have 4, 1, 2, 3. And now, of course, we're accessing page 5, which was what we just kicked out. So now our oldest one is page 1. So now we would kick that out again. And now we have 4, 5, 2, 3. So we did pretty much the worst thing we could do. And in this case, we have 10 page faults. So we only got 2 page hits, and then we kept on going through the cycle of accessing the page we just kicked out. And you can see when you do this, an easy way to look at it is, hey, all the page fault ones go in kind of like a waterfall pattern there. So they're nice diagonal lines, so they should all look like that. If you're doing first in, first out, makes it easier to track a little bit. So 10 page faults compared to 6, that is pretty bad, and probably the worst we'll see all day. Now let's see something fun. So let's do the same example. So here we hold 4 pages. So if our memory held 5 pages, we would be pretty much okay. We would have 5 page faults, and then everything else would fit essentially, right? So we'd have 5 page faults, then everything would be in memory, it would all fit. So it stands to reason that if more pages are better for the number of page faults, then the fewer pages we have, the more page faults we have. That would stand to reason that less pages we have to work with, the more page faults we have. So let's reduce it. So we'll do FIFO, but now instead of 4 page frames in memory, we only have 3. So now we have 3 instead of 4. So on our first access, of course, we have 1. That is a page fault. So we load it into memory, and now memory contains the first page. Then access to 2, same thing is going to happen. Then access to 3, and the same thing is going to happen. And now we have an access to page 4. So what should we replace with page 4? 1. So if we do our waterfall thing or whatever, we can look. 1 is the current surviving one, so that's the one that should go. So we would replace 1 with a 4. So now we have an access to page 1. So this is looking really bad. So we already have more page faults than we had before. We are 0 for 4 on this case. So we have an access to page 1, and that's a page fault. And what are we going to replace? 2. So 2 is the next oldest one. So we would replace a 1 with a 2. Oh no, our next access is to page 2 that we just kicked out. So now we're going to load in page 2. So in this case, our oldest one is page 3. So we're going to kick out page 3. So with our access to 2, we kicked out page 3. So now we have 4, 1, 2. Okay, yeah, this is looking pretty bad. We got 6 page faults all in a row. Not great. So now we have an access to page 5. It's going to be a page fault 2 as well. What are we going to replace? 4. So 4 is our next oldest one. So we replace 4. So now we have 5, 1, 2. Okay, and now our next access is to page 1. It's in there. We're looking good. We got our first hit. And now we're going to get super lucky again because our next access is to page 2, which is also in there. So that's pretty good. Now we have an access to 3. So what's getting kicked out? 5, 1. So between all the pages that are currently in there, 1 was the latest one to go in, so it is out. So we replace 1 with a 3. So we have 5, 3, 2. Then we have an access to page 4, which is also bad. So we're going to have to replace something, and in this case, we're going to replace 2. So we'd have 5, 3, 4, and then our last access is to page 5, which is a hit. And how many page faults do we have? Weird. So we have 9 page faults, which is actually better than when we had 4. When we had 4 frames and we had more memory, we actually had more page faults. Kind of weird. So there's a name for this. It's Belladie's anomaly. And it says for first in, first out, it says more page frames, paradoxically, cause more page faults. And this is a problem with all FIFO algorithms. It does not exist for LRU, or least recently used, which is that history-based ones, or any kind of stack-based algorithms that we probably won't see. So there's a paper about this if you're like really into math that you can read, and it basically says you can construct any arbitrary sequence to get any arbitrary page fault ratio you want if you can craft it yourself. So that is fun for some late night reading if you want to put yourself to sleep. And so, thankfully for other algorithms, increasing the number of page frames, like increasing the size of your memory, actually decreases the number of page faults, which is what you would actually expect. This is only the case for FIFO algorithms, and it's this weird anomaly. Yeah.
So in the previous example, you said if there were five pages,
Yeah.
that would increase more page faults?
So in this one, if we had 5 in this example, we only have 5 accesses to 5 pages, so they'd all just load in. So we'd just have 5 page faults, and then everything would be in memory.
Okay, so that paper is not true all the time.
Yeah, you have to like be able to swap things in. In that case, it all fits, so you never have to swap anything. So the paper is like, if you have to swap anything, you can construct an arbitrary sequence that makes it terrible. Okay, so let's try a LRU, or a least recently used policy. And in this case, we'll use FIFO to break any ties we have where they would be, which seems a bit weird that you'd use FIFO to break ties in least recently used with only one CPU and one thing doing accesses. So that would only be the case if you actually had like multiple CPUs and you could actually get a tie. But in these scenarios, we essentially can't get any ties. So let's go back and we'll make our memory be able to hold 4 pages. And we'll do the same accesses again. So the first 4 are going to be boring. They're going to all be page faults. So we're going to have 1, 2, 3, 4. And then we're going to access, our next accesses are to page 1 and 2, which are currently in memory. So they are both hits. And the only difference is going to be when we access page 5. So when we access page 5, what should we kick out? So if we do least recently used, well, that's going essentially back into history. So most recently used is 2, since that was the previous access. So 2's safe, I shouldn't touch 2. And I also shouldn't touch 1 because it was used after 2. And then going back, I also don't want to touch 4. So between 1, 2, 3, and 4, my least recently used is number 3. So if I'm doing least recently used, I should kick out 3. So when I do the access to page 5, I'm replacing page 3. So now in memory, we have 1, 2, 5, and 4. And again, this is just using the fact that generally, if you access some memory, you're going to reuse it again soon after that. So this is trying to take advantage of that. So luckily, it paid off because our next access is to page 1, and we didn't replace it. So that's good. Our next access would be a hit because we access page 1, it's there, and then we access page 2. So if we access page 2, it's also still there. That is a hit. And now we're slightly unlucky. We're accessing a page 3, so we have to kick something out. So again, we look back into history to see what is the least recently used. So Page 2, if we go back, was most recently used because it was our last access. Subsequently, 1 is also safe because it was used after that, and then 5 is also safe. So the number that's currently in memory that's not 1, 2, or 5 is 4, so we kick that out. So we kick out page 4 with page 3, and oh no, our next access is to page 4. So if our next access is to page 4, again, we have to swap it in, and we'll go look back at history. So if we look back our history, our 3 most recently used pages are 1, 2, and 3. So we would keep all those and replace 5 with 4. So now we just kicked out page 5, which was a bit unlucky because our next access is going to use page 5. And at this case, and now when we have page 5, our least recently used is going to be page 1 because the 3 most recently used ones are 2, 3, and 4, so they're all safe. So we would kick out 1. So that's our last page fault. We replace 5 with a 1. So now if we go ahead and count all of the page faults, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 page faults. So that was better than our first in, first out, which was 10. And first in, first out with 3 pages is only 9. Here, at least, was better than with only 3 page frames, but not quite as good as 6. All right, any questions so far? Fairly straightforward, which is a nice break. So, if you implement least recently used in hardware, you're going to have to do what we did in the example, which was search all of the pages to see when it was least recently used. So if you actually have to implement something like this, you could use a timer or a counter on each page that keeps track of when it was least recently used. So whenever you reference a page, you would have to update that, hey, it's been used recently. So every time you access a page, you would have to update that timer on that page. So your operating system essentially knows not to touch that anymore. And then whenever you have to kick out a page, you have to scan through all the pages to find the one with the oldest clock, which would be slow. You might be able to speed it up a little bit by using a, like a red black tree or something like that. But it's still going to be fairly slow. And the worst part about this is on every page reference, you have to write some memory into like a clock that keeps track of it. And if you do that for every single page access, which is essentially every single memory access on your machine, you're probably going to make it twice as slow. So that's not going to work. It's going to be way too expensive. You could also be like, hey, well, I'm smarter than that. Instead of doing just a counter, I could just create a doubly linked list of pages that has a front and a back. So whenever I have a page reference, I'll move it to the front of the list and say, hey, it is now the most recently used page. And then whenever I want to replace the page, I just pick whatever's at the back of the queue, which is like 01. But this 01 actually matters as well. So for each of them, there's like 6 pointers updates for each page reference. And it also creates really high contention and bottleneck if you have multiple processors. So all those pointer accesses are going to have to be essentially guarded with a mutex. So it's going to be all serial. And if you have 6 pointer updates for every 1 memory access, it's going to be terrible. And even more terrible if you have to acquire a lock with it. So in practice, it's not going to work at all. So what we're going to do is settle for a approximate least recently used, and that is generally okay because least recently used is an approximation of the optimal case anyways. So an approximation of an approximation is exactly what makes good engineering. So there's lots of different tweaks you could do to implement it more efficiently. So next lecture, even though usually this one takes more time, but I guess we can end early. So next lecture, we'll look at the clock algorithm, but there's also a few different variations. There's least frequently used, which is a slightly bit different. There's a 2-queue approach, and there's an adaptive replacement cache that we won't see. But there's a bunch of different options, and there's generally, like scheduling, there's no right answer. It's just a series of trade-offs. So, any questions today? Or everything fairly straightforward? Generally, page replacement is like a nice little break. So we have midterms today, so we can just wrap up. We are hella early. It's tomorrow? Oh, well, we can study, or we can take a time and we can start lab 4, and you can probably like finish most of lab 4. So page replacement was all the algorithms. There's only one metric you use, and it's the number of page faults, and that's what you aim to reduce. So we saw the optimal algorithm, which is you just replace whatever's not used in the future the longest, so that's good for comparison. Obviously not realistic because we can't predict the future. And then there's random replacement, which we didn't see an example of because it's just random. It actually works surprisingly well. It's better than first in, first out because it avoids the worst case scenario. And then FIFO is easy to implement, but it has that Beladies anomaly, which is really weird, where reducing the memory actually reduced the number of page faults. And there's that weird paper that says that's true. And then there was least recently used that gets close to optimal, but easy to implement. So hopefully this is a nice break. So just remember, I'm pulling for you. We're all in this together.